In this video, we're going to introduce the redox table that is in your data booklet on page 7. We're going to go over the spontaneity rule as well as do a lab to see the reactivity of metals and their ions so that we can start building our own redox tables. So, a redox table, what it is a list of reduction half reactions. Okay, so that's reading it from left to right. Okay, and now these half reactions, they're placed in a special order. You're going to have your strongest oxidizing agent, which I'm going to abbreviate to SOA, is going to be at the top left of the table, and the strongest reducing agent, which I'm going to abbreviate to SRA, is at the bottom right of the table. Okay, so if we go to our data booklet and take a look at this, so it's on page 7. So here's what it is. Okay, so it says reduction half reactions, and again, that's if you read it from left to right. So as we just said here, our SOA, so our strongest oxidizing agent, is going to be in the top left-hand corner. So fluorine here, that is our strongest oxidizing agent out of this entire list. Okay, so one thing to be mindful of with this table here is you got to understand that all of your oxidizing agents, they're all on the left-hand side of the reaction arrow. So if I was to highlight this really quick here, all of these, I'm not going to highlight the electrons, but all of these on the left-hand side, these are all oxidizing agents. Okay, so the reason why I'm going through and I'm highlighting each one is just so that you can see all of these on the left-hand side are the oxidizing agents. Okay, and since our strongest one is in the top left-hand corner, as we go down, okay, they get weaker and weaker and weaker. So lithium 1+, that is going to be your weakest oxidizing agent. Okay, now alternatively, if we are talking about reducing agents, one thing that you have to understand is all of your reducing agents, they're going to be on the right-hand side. Okay, so all of these are your reducing agents. So do you have to go through and highlight every single one of these in your own data booklet? No, you don't, but this is just to help you visualize where your reducing agents are. Now, reducing agents are going to have the opposite trend of oxidizing agents. So your strongest reducing agent is going to be in the bottom right-hand corner. So lithium is our strongest reducing agent. Okay, so essentially what this means is, remember, oxidizing agents here, they oxidize other things. However, they themselves undergo reduction. Now remember, Leo the line goes grr, gaining electrons is reduction. Okay, now what this is saying is something that's really bad at gaining electrons, okay, or being reduced, is actually really good at losing electrons. Okay, that's why the oxidizing agents have the opposite trend as the reducing agents in redox tables, okay? Because something that's really bad at gaining electrons would be really good at losing electrons. Conversely, something that's really bad at losing electrons is going to be really good at gaining electrons. Okay, so the trend here is as we go up this table here, the reducing agents get weaker and weaker. Okay, so the fluoride ion right here, that's going to be your weakest reducing agent in this table here. Okay, so the main ones that you need to make sure that you know the location of, that's going to be the most helpful to you, is you need to understand or know where your strongest oxidizing agent is and where your strongest reducing agent is. You need to know the locations of those. Okay, and that's so that you know the general trends of the oxidizing agents, how they're getting weaker as you go down the list, and then for the reducing agents, the strongest one is in the bottom right, and as you go up on the right hand side of the reaction arrows, those reducing agents get weaker and weaker and weaker. All right, so these redox tables, they're listed in that special order. With the left-hand side, you go from your strongest oxidizing agent at the top, and they decrease and they get to the weakest oxidizing agent at the bottom left there. With strongest reducing agents, the strongest one is at, with reducing agents, the strongest one is at the bottom right, and they get weaker as you go up. Okay, so that special order of your redox table is very important because it tells you if a reaction between two different substances is going to be spontaneous or not. So a reaction will spontaneously occur between an OA, so an oxidizing agent, and an RA, reducing agent, as long as the OA is higher on the table than the RA. So that's going to be really important here. Okay, because that's going to help us to determine whether a reaction is spontaneous or not. So remember that the electronegativity is the relative tendency for an atom to attract a pair of bonding electrons. Elements with high electronegativities are typically strong oxidizing agents. Okay, so remember, oxidizing agents, they help other things get oxidized, but they themselves undergo reduction. Reduction is a gain of electrons. Okay, so if you're really good at attracting bonding electrons to yourself, it makes sense that you're also really good at gaining electrons. Okay, meanwhile, strong reducing agents, they are going to have low electronegativities. Okay, which makes sense. Reducing agents undergo oxidation when they help something else to get reduced. Okay, so they themselves undergo oxidation, which, if we remember Leo the lion goes grr, Leo, loss of electrons is oxidation. So reducing agents lose their electrons when they undergo oxidation, so they're really good at giving away their electrons, and they can only do that if they have a low tendency to attract bonding electrons to themselves. So if they have a tendency to have low electronegativities. Now, for spontaneity, in order to determine whether a reaction is spontaneous or non-spontaneous, we need to use the following guide. Okay, so when the OA oxidizing agent is above the reducing agent, the reaction is spontaneous. However, when the OA is below the RA, the reaction is non-spontaneous. Okay, so your relative positionings of your OAs, which is oxidizing agents, and your RAs, which is reducing agents, that's going to tell you whether your reaction is spontaneous or non-spontaneous. So remember on the table how I said all of your oxidizing agents, they're on the left-hand side of the reaction arrows. Okay, and I'm just going to do a little drawing to represent the spontaneity rule. Okay, so if your OA is above your RA, right, so I'm drawing the RA on the right-hand side because all of our reducing agents in our table, they're all on the right-hand side of the reaction arrow, so they're highlighted in pink. Okay, so if your OA is above your RA, you can kind of remember the spontaneity rule by thinking of like a ball rolling downhill. You don't have to push that ball in order to get it to roll downhill. You just have to let it go and it'll roll downhill. Okay? So this is spontaneous. However, if we do a similar drawing, except for the OA is below the RA, you could think of a ball rolling uphill. That's non-spontaneous. You have to put energy into it. You have to roll that ball up the hill in order to get it to the top. Okay? So same deal with spontaneous and non-spontaneous reactions. A spontaneous reaction just goes, whereas a non-spontaneous reaction, you have to add energy to it, whether that's heat or maybe it's electricity. You just have to add energy in order to make it go. Okay, so that's how you can remember the spontaneity rule here to help you determine if a reaction is spontaneous or non-spontaneous. So this is very important. Okay, so we've got some practice questions here, but I want to move on to the next page here that's talking about a lab setup here. Okay, so in my video here, I have a slightly different setup than what they're talking about here in the diagrams, but I'm still going to be using the same chemicals. So I'm still using copper 2 nitrate, zinc nitrate, magnesium nitrate, and silver nitrate. So what you're going to do is you're going to watch the video and you're going to fill out this table. So with the copper 2 plus ions, that's talking about the copper nitrate solution there. Okay, so when you see the setup between copper nitrate and all the different metals, so the different metals are copper, zinc, magnesium, and silver, okay, you're going to fill this first column out when it talks about copper 2 nitrate reacting with all the different metals. Okay, for this next column, you're going to fill it out when it's talking about the zinc nitrate solution reacting with the same metals there, the copper, zinc, magnesium, and silver. This one will be the magnesium nitrate solution, and this will be the silver nitrate solution. So what you're going to do is you're going to put a check mark if a reaction occurred, okay, and I go through in the video whether a reaction occurs or not. Okay, and if a reaction does not occur, then you're going to place an X. Okay, this one's copper. So as you can see, there's no color change here, so there was no reaction between copper and copper nitrate.
This here is zinc. So we'll leave that in for a bit, and I'll put this back in here too. Okay. Here's magnesium. And here's silver. We've got copper, and this is in magnesium nitrate, or this is in zinc nitrate. Here's the zinc. Here's the magnesium. And here's the silver. So with the copper, there's no reaction that's happened. With the zinc, there's also no reaction that's happened. Oh, maybe if I... So no reaction there. With the strip of magnesium, you can kind of see like a lighter color there. Okay, so this lighter color means that this has reacted. With our strip of silver, it is not reacted. Copper. This is our zinc. Here's our magnesium. And here's our silver. So copper, no reaction. Zinc, there's no reaction here. Magnesium, also no reaction. And then silver, no reaction. So here we have our copper. We have our zinc. So here you can already see that the copper is reacting. Here's our magnesium. And then here is our silver. So as you can see, the copper's reacted. The zinc has reacted. You can tell by the color change. The magnesium's reacted, but you can also see that there's little bits of product floating around in this beaker now. Okay, and the silver has not reacted.
All right, so after that video, this is what your table should look like here. All right, so we're gonna answer the next few questions here using our table. So what symbol did we use for a spontaneous reaction? We used the check mark, and for the non-spontaneous, we used the X. Okay, so what do we notice about the spontaneity or not of the metal reacting with its own aqueous solution? Okay, so if we look at our table here, these are the ones where the solid metal is reacting with its own solution. So as we can see, the metal did not react with its own ions in solution. So let's write that out. No reaction, which I'm going to abbreviate to RXN. A metal will not react with its own aqueous ion so this will always be non-spontaneous. So I'm going to abbreviate non-spontaneous just to non-spon. All right, so example number 3. Is this reaction spontaneous or non-spontaneous? So we want to focus in on the reactants and see where they are on our table here. So let's go back, and I'm going to get rid of these blue circles. Okay, so we're checking it out in between our copper 2+ solution and magnesium. So this one and this one. So I'm just tracing my finger and I'm saying, okay, yep, it reacted. It was spontaneous. So let's write that in. It was spontaneous. Okay. For the next one, okay, reaction between copper solid and magnesium ions. Is that spontaneous or non-spontaneous? So let's check that out. So copper solid is here, magnesium is here, so that was non-spontaneous. All right, next one. Is this reaction spontaneous or non-spontaneous? So solid zinc with silver ions, let's check that out. So zinc is right here, silver ions, so there it is. Okay, so this is going to be spontaneous because we have that check mark there. Okay, now is this reaction spontaneous or non-spontaneous? Okay, so something you should notice about these reactions is notice how for the first question they're giving us, so let's look at this one, the products that they had for the spontaneous reaction are the reactants for the non-spontaneous reaction. Okay, so just make sure you notice that. Okay, now for zinc 2+ and silver solid, okay, maybe you've already guessed that, but let's check out our data table here. Okay, so let's get rid of that. Okay, so magnesium, oh, nope, that's silver. Silver solid and zinc. that was non-spontaneous there, okay? So that's going to be non-spontaneous. All right, so based on our observations in question 3A and 3B, do we think that this statement is true or false? If the forward reaction is spontaneous, then the reverse reaction will also be spontaneous. Well, let's look at these again. Okay, so I already talked about this first one here, but let's talk about these next two here. Okay, so for the spontaneous reaction, the products that we got out of it were the reactants for the next reaction. So what we can see here is that when we have a reaction going from solid zinc and reacting that with silver ions, that reaction is a spontaneous one. But if we try and go backwards, okay, so we have our zinc ion and our solid silver producing our solid zinc with silver ions, that's going to be a non-spontaneous reaction. Okay, so you could think of these as the same reaction. One's just the forward version of the reaction, and the other one's the backwards version of the same reaction. Okay, how I know that is because the products here are the reactants here. That's how I know one is the backwards version of the other. So looking at this sentence, if the forward reaction is spontaneous, then the reverse reaction is also going to be spontaneous. That's not true, because we just saw in these two cases here that if the forward reaction is spontaneous, the backwards reaction is going to be non-spontaneous. All right, so if false, we need to make it so that it is true. So the reverse reaction will be non-spontaneous. So that's how we would make this true. All right, example number 5. We've got to list the metallic ions in order of their tendency to form metals from greatest to least. So in other words, list the metallic ions in order from most reactive to least reactive metallic ion. Okay, so we got to go back to our data table here. Okay, so since we're focusing on the ions here, I'm going to be reading each of these columns. Okay, so looking at the copper 2+ column here, I see that the copper 2+ ion reacted a total of 2 times, right here and right here. Okay, so I'm just going to make a little note to myself. The zinc 2+, it only reacted once here, so I'm just going to go 1. Magnesium didn't react at all, and then silver reacted 3 times. Okay, so I'm getting my order now. So it looks like the silver ions are the most reactive, then copper ions, or sorry, copper 2+ ions, then zinc ions, then magnesium. Okay, so let's order it. Okay, so what's happening with these ions is essentially what's happening is they are going from, I'm just going to use X for a placeholder for an element, and since all of these are 2+, I'm just going to go with 2+. Okay, so when they react, they're going from an ion to a metal. Okay, so they're going from aqueous to solid, right? And how one can do that, if we balance this half reaction, remember from the previous lesson, in order to balance a half reaction, you have to add electrons to the more positive side. So this has a 2+ charge overall on the reactant side. The product side has a 0 total charge, so I gotta go over here and add 2 electrons. Okay, so remember, when you see electrons on the reactant side, that's telling you that the electrons are being gained. Okay, so electrons, or it gained electrons, and gaining electrons we know is reduction. Okay, so remember, Leo, the line goes grr. Grr is gaining electrons is reduction. Okay, so this tells us if it's being reduced, then it's an oxidizing agent. Because remember, oxidizing agents help other things to be oxidized, but it itself undergoes reduction. Okay, so if these metallic ions form solid metals, are they behaving as OAs or RAs? Well, answer is OA. Okay, or oxidizing agent. So the next part, we need to list the metals in order of their tendencies to form positive ions from greatest to least. So in other words, list the metals in order from most reactive to least reactive. So let's go back to our data table here. Okay, and what I'm doing is I'm reading the rows. Okay, so I'm reading the rows and I'm just going to notice. Okay, copper solid. We only had one check mark in this row, so it only reacted once. With zinc, we've got 2 check marks, so it reacted twice. Magnesium, it reacted 3 times, and then silver didn't react at all. Okay, or the silver solid. Okay, so let's use that to order our list. It looks like magnesium reacted the most, then zinc, then copper, and then silver. All right, so if these solid metals form metallic ions, are they behaving as OAs or RAs? So let's just do a little sample reaction here, just like we did before. Okay, so we have some element, which I'm just going to say is X, okay, going to some positively charged ion, which, because everything had a 2+ ion, I'm just going to say 2+ here. Okay, and we're going to balance our half reaction, so we're adding electrons to the more positive side. All right, so whenever you see electrons on the product side here, that's going to be a loss of electrons. Okay, so the solid metal had to lose electrons. So losing electrons, Leo, the line goes grr. For Leo, losing electrons is oxidation. Okay, so what type of agent undergoes oxidation? Well, that's going to be a reducing agent. Okay, remember, reducing agents help something else to get reduced, but it itself undergoes oxidation. Okay, so these solid metals, they're undergoing oxidation. Okay, and they're acting as reducing agents. So as they help something else to be reduced, they themselves are being oxidized. All right, how do the lists in question 5 and 6 compare? Do you know why? All right, so let's take a look at them. So I'm noticing, okay, silver was the most reactive ion, but it was the least reactive metal. And magnesium, that was the least reactive ion, but the most reactive solid metal, okay? And then essentially what I'm seeing here is that question 5, what we came up with, that is the opposite trend as what we got in question 6. Okay, so how do they compare? They're opposite trends. So if the ion is highly reactive, the metal is unreactive or reacts very little. Okay, so why does this happen? All right, so let's go back to the ions. I want to focus in on silver. So silver would be in this spot in our template. Okay, so silver was super reactive. Okay, what that tells me based off of our template reaction here is that silver ions, they're very good at gaining electrons. So if something's very good at gaining electrons, it's going to be absolutely terrible at losing those electrons. Okay? Similarly, if something is terrible at gaining electrons, it's going to be wonderful at losing electrons. Okay, so there's that opposite trend there. Okay, if something's great at being reduced, it's going to be awful at being oxidized. If something is great at being oxidized, it's going to be awful at being reduced. Okay, so let's build our own little redox table based off of our data. Okay, and we've kind of already organized the information in question 5 and 6. Okay, so our strongest OA, we said that the ions here are acting as oxidizing agents, or OAs. So I'm going to use this list in question number 5, and I'm going to use the most reactive metallic ion. I'm going to put that at the top because it was most reactive, so it was our strongest OA. So silver, 1 plus, copper, 2 plus, zinc, aqueous, and then magnesium, 2 plus. Okay. So magnesium ions, they are the weakest OA because they really didn't react that much. Okay. All right. For our reducing agents, the most reactive metal, so our strongest reducing agent was magnesium solid. Okay. Whereas our least reactive metal, so our weakest reducing agent, was silver. So remember your strongest RA, that's going to be in the bottom right hand side. And let's color code this. And sure, let's do pink. All right. So now that we have that done, just notice that this is starting to follow the same trends. It's just on a smaller scale, but it follows the same trends that is in our redox table on page 7 of our data booklet, okay, where our SOA is in the top left and our SRA is in the bottom right. Okay, so we're kind of building our own little redox table. Okay, so notice that we can take the two tables of reactivity and combine them just into one table here. Okay, so we have all of our reduction reactions where all the electrons are being gained. How we know that is because they're on the reactant side. Okay, whereas with this other side here, everything's undergoing oxidation, and how we know that is because all of the electrons are on the product side. Okay, so the high reactivity reactions are at the top, and then they get weaker and weaker as we go down for both of these tables, or both of these lists. Okay, so when we combine them, this is what we're going to get. Okay, so silver ions, those are our strongest oxidizing agents. for this specific table with our small set of data. Okay, and our magnesium solid, that's our strongest reducing agent. Okay, so for our strongest, or for our oxidizing agent, the strongest one starts at the top, and it gets weaker and weaker as you go down the left-hand side of the substances here. Okay, the reason why I'm specifically saying only the left-hand side of these substances is because only on the left-hand side of the reaction arrow is where your oxidizing agents are. Meanwhile, the right-hand side, those are where all of your reducing agents are. Okay, so as you start from the bottom, okay, you start at your strongest reducing agent, and then you go up. They get the reducing agents on the right-hand side of the reaction arrow get weaker and weaker and weaker. Okay, so the reducing agents, they decrease order and tendency to lose electrons, whereas the oxidizing agents, going from top to bottom, decrease in order of tendency to gain electrons. Okay, so your strongest oxidizing agent is most readily reduced, and your strongest reducing agent is most readily oxidized there. Okay, so that's what you should know about your strongest oxidizing agent and your strongest reducing agent. This is what we're meaning here. So what this is trying to get at is this is how redox tables are set up. Your SOA is always going to be in the top left-hand corner. Your SRA is always going to be in the bottom right-hand corner. Okay, so moving on to example question number 1. So we're given data this time around, and we got to use the data from the table as well as the key. So the key's over here. Below to rank the oxidizing agents from strongest to weakest. All right, so we have our ions as well as our solid metals. Okay, so the ions, if we look at beryllium here, we're going from a 2+ charge to a 0 charge, right? So you can only do that by gaining electrons. Gaining electrons is reduction, okay? And things that get reduced are oxidizing agents, okay? And we were asked to rank the oxidizing agents. So that means you're ranking the ions, because those are your oxidizing agents, because they're the things that get reduced. They help something else to get oxidized. Okay, so the check mark indicates evidence for a spontaneous reaction. So we want to figure out, okay, which one of these ions went through the most spontaneous reactions here. So I'm just going to do what I did before and just count up. So beryllium, 2+ only went under 1 spontaneous. Cadmium, 2+ was 3. Radium 2+ didn't do any spontaneous reactions, and vanadium went through 2. Okay, so there's my rankings there. Okay, so we want to say cadmium, and then vanadium, and then we've got beryllium, and then we got radium. Okay, but we got to use the key so that we can put in the answer. So this is a style of diploma question that you will see, but sometimes they don't always give you the identity of the substance here. So just watch out for that. So cadmium, that was 4, and then vanadium, that was 8. Beryllium was 2. Radium 2+ was 6. Okay, So what you can do just to break these questions up to help yourself out is write out what you're aiming for your answer to be is, and then like match up whatever numbers to those substances that was given in the key. All right, example number 2, we've got to rank the reducing agents. So reducing agents, they undergo oxidation. So they like losing electrons. So these are going to become more positive. Okay, so with that, that's how you can figure out that our reducing agents, so let's look at zinc. So zinc starts at 0, and then we have it as a 2+ charge. So going from a solid to an ion, an aqueous ion, we get more positive because we go from a neutral or a 0 charge to a 2+ charge, right? You can only do that by losing electrons because you're gaining, or because you're getting a more positive charge. Okay, so because zinc solid has to lose the electrons in order to become zinc 2+, that's how you know the solid metal is your reducing agent. So I'm going to be reading the rows here this time around. Before it was the columns. Okay, so for zinc, looks like it went under 2 reactions. Vanadium, 3, cadmium, that's going to be 1, and then lead didn't do anything. Okay, so we're ranking it from strongest to weakest, so most reactive to least reactive. So let's just do this stepwise. So vanadium was the most reactive, then zinc, then cadmium. Oop. There we go. And then lead. Okay, so let's use our key to figure this out. So where's vanadium? Vanadium's number 7. Then zinc solid is number 1. Cadmium is number 3. And then lead solid's number 5. There we go. Okay, and to wrap this up, what is the spontaneity rule? So that's the rule that says if your OA is above your RA, you will have a spontaneous reaction. So RXN is just my shorthand for reaction. If OA is above RA. Okay, and if the OA is above the RA in the redox table. Okay, that's what it's referring to. Okay, meanwhile, if you have your your OA below your RA, you're going to have a non-spontaneous reaction. Okay, so one last little thing here to remember is if your forward reaction, or if the forward reaction, I should say, so if the forward reaction is spontaneous, then the reverse reaction will be non-spontaneous. Okay, And that works vice versa. If your forward reaction is non-spontaneous, then the backwards reaction would be spontaneous.